Hey guys, welcome back, and now we're going to be talking about optimization. And before we get started, I hope you guys watched my first video on word problems because it's going to help you a lot when it comes to optimization problems and breaking down the word problems in optimization, which usually is the hardest part. So other than that, let's go ahead and get started. So optimization is actually the application of maximum and minimums, right? And you guys know that we find maximum and minimums by computing our first derivative test, right? So we're going to be computing a lot of first derivative tests when we do optimization problems, right? But it's actually going to be the simpler part of optimizations. The harder part is working with the equations, breaking down the word problems, and getting our answer, right? So when doing this, we're actually going to have to use multiple equations, right, to find our solution. So usually means that not always, but most of the time, we're going to have to work with two equations to get our answer, right? So be expecting to have two different types of equations. We're going to play with them and see what equation we actually need to work with. But before we talk about that, let's go ahead and say what optimization is, right? Optimization is actually one of the most real applications of calculus due to the fact that, for example, if you're a business owner, you're always trying to minimize costs and maximize profits, right? And that's exactly what maximum minimums are about, finding maximums and finding minimums, right? But in order to break down these word problems that we have, I have developed a little step box for us to follow, right? The first step is going to be just read the problem, right? You have to read the problem and use a diagram to help you, right? That's going to be step one right here. You're going to use a diagram to help you. Then after that, you're going to write down your given information. All given information means numbers, equations, or even the third part, what are you actually even trying to maximize or minimize in your problem, right? What exactly are you trying to do? And then after that, that's going to be the tricky part, in which for number 4, we're going to be using multiple equations, but we're going to write the equation in terms of one variable, right? Which means that when we're maximizing, we need to take a derivative, right? But we like taking derivatives in terms of one variable so that we can set that equation equal to 0 and perform our first derivative test, right? So after we do steps 1 through 4, which are the harder part of breaking down the problem, we go ahead and do our first derivative test, right? So the first derivative test is actually the easiest part of optimization. The hardest part is actually getting to the point where we're about to perform the first derivative test, right? So it's enough talking about optimization. Let's go ahead and get started on an example. So let's say you're Mike, and Mike wants to build a rectangular pen using 500 feet of fencing, right? So let's just stop right there and break down this problem. You want to build a rectangular pen. So that's why I drew a rectangle for you guys. Well, I kind of used the computer because I suck at drawing, so I wouldn't want to hurt your eyes. And then you have 500 feet of fencing to build this rectangular pen, right? So that's given information. Here I have that if I have 500 feet of fencing, that means that I can only use 500 feet to border my rectangle, right? So let's think about what that means, that I only have 500 feet to border my rectangle. I'm just going to leave that there. You guys think about it for a second. And what dimensions will maximize the total area of the pen, right? Cool. So let's go ahead and write what we have. We have 500 feet of fencing, right? And we want to maximize our area, right? But how do we find area? Quick formula for area is going to be x times y. X times y. You guys could have gone with base times height, width times length, whatever you guys are into. I'm going to go with x and y, right? And I'm trying to maximize my area, right? Which means I'm going to try to derive my area, right? So I want to derive my area and perform my first derivative test, but it's just not that easy. I can't just get right into it, right? I need to actually go through another equation to try to get myself there. So what that means is that I'm going to go ahead and have to use the given information, which is 500 feet of fencing, okay? So if I have 500 feet of fencing, what I need to do is I need to go ahead and think about what that means and what equations that relate to. And whenever we talk about fencing, these problems are going to be very common in optimization. The fencing part refers to the perimeter that we have, right? Since we can border the rectangular area with 500 feet of fencing, we're talking about its perimeter, right? So real quick, let's just go ahead and write down our perimeter formula, right? And our perimeter formula, which I'm going to do all that in blue, just to change the color. right? My perimeter formula is going to be, if I add up all the sides, right, I'm going to have another x here, I'm going to have another y. So I'm going to have a total of 2 x's and 2 y's for my perimeter, right? 2x plus 2y for my perimeter. And that is all going to be equal to 500. So 500 is equal to 2x plus 2y. Okay, but now what do I do with this, right? What am I trying to do? I'm trying to maximize my area, right? I'm trying to maximize this area, which means I need to do my step 4, which I need to write my equation in terms of one variable. And in this case, my area, which I'm trying to maximize, is in terms of x and in terms of y. Big no-no, one of them has to go away. So I'm usually taking first derivative test in terms of x, right? We usually have a function in terms of x, and then we just take the first derivative. But we're not always going to get that lucky that we can do it, because it might just change up in the problem. But here, it looks like I can try to go for it, right? And I'm going to go ahead and solve for y, so I can change this y in terms of x, right? I'm going to solve for y over there, so I can change that y in terms of x. So if I do that, before I even solve for y, I can just divide every term, the 500, the 2, and the other 2, these 3 terms, I can divide them all by 2. So I'm going to have 250 x plus y. And I'm still trying to solve for y, so I'm just going to move over this guy to the left. And that is going to go like this. 250 minus x is equal to y. So now that I have solved for y, I'm going to go ahead and plug this y into here, right? Leaving me with a new formula, which is going to be a is equal to x times 250 minus x, right? So now I have my new formula in terms of one variable. So now I've written my area equation, which is my equation I'm trying to maximize in terms of one variable. And that is going to be like, you're just 70% there. Once you have done that, you're almost good to go, because you figured out what's going on in the problem. You were able to draw it out, right? And then you can be like, okay, I'm trying to maximize this area. This is what you're trying to do. You're trying to get the most area inside, limited by your perimeter or your fencing, right? So let's go ahead and just do that, right? I'm going to have to take the derivative of the area. But before I even do that, I'm going to go ahead and distribute this, just so I don't have to do it in a necessary product rule. I'm just going to have 250x minus x squared. Cool. And now I'm going to go ahead and derive. So I am ready to jump into step 5, which is finding my first derivative test, right? So now that I have breaking everything down, I'm ready for the first derivative test. Let's go ahead and do that. So I'm going to go with a prime. I don't need a prime of x, just a prime. Derivative of 250x is just 250. Derivative of x squared is just 2x. And my first derivative test goes like this, right? After I take the first derivative, I go ahead and set it equal to 0. So I'm going to go ahead and set this equal to 0. So I'm going to have 250 minus 2x equal to 0. I'm going to move over the 2x. I move this guy over. And I'm going to derive both sides by 2. So I divide this side by 2 and this side by 2. So then I get x is equal to 125. Okay? So I have x is equal to 125. So I have found myself a critical number, or a possible dimension of my x to maximize my area. But I need to perform the first derivative test still, which means that I'm going to check if this is actually a maximum or a minimum, right? Although I'm trying to maximize, I'm looking out for maximums. So let's go ahead and have my first derivative number line. Put my critical number in there, 125, and see if that's my actual maximum, my dimension to get my maximum. So if I put 125 there, I'm going to pick a number less than 125, simple, 100, and something bigger than 125, so I'm going to go with 200. So if I plug in 0 into my first derivative, which is right here, I'm going to get a positive number. And if I plug in 200, I'm going to get a negative number. So since I'm going from positive, I can actually put that right here. If I'm going from positive to negative, that shows that at 125 I have a maximum, right? So I'm going to upgrade my x equal to 125 to being x star, right? Which means that is my x coordinate to find my maximum area. But I have just gotten my x dimension. I need to actually get my y dimension. So real simple, I already solved for y over here. So what I need to do is I need to plug into y to get my y star, which is my dimensions for my maximum. So I'm going to have 250 minus 2 times 125, right? And this is actually just a quick reminder. This right here is x star that I'm plugging in. So I'm going to have 250 minus 125. 250 minus 125. Oops, I don't know where that 2 came from actually. But that is going to be a total of 125. Alright, so my dimensions here are actually x and y are equal. Both my x star and my y star are the same. So the dimensions that maximize my total, the area of the total pen would be x being 125. So your base being 125 and your height being 125 as well. So we have just maximized. We have found the maximum area, the dimensions of the maximum area. So now let's go ahead and do another example. So I can ask you 2 questions on this, right? I can ask you, what is the maximum area? What are the dimensions of the maximum area? I decided to ask you what are the dimensions, right? If I would just ask you what the maximum area is, I would just multiply my dimensions together. So there's not much work to do there. I just multiply them together, which that would be my a star, right? Multiplying my x star to my y star. But I only asked you to find what my dimensions are. So now let's go ahead and do another example where we have Mary who needs to make a rectangular box, right? So I went ahead and drew that for you already, courtesy of Microsoft Word, with a square base of 48 feet. With a square base from 48 feet of material. Cool. So what does that mean? So it means I want to make a box. It has a square base, so it means that this length and this length are going to be equal. I went ahead and made those x already because I like working with x and y, so if I can. And then I'm making this from 48 feet of material. Kind of tricky. But I'm going to have my square base. That means that this right here and this right here are equal, right? I'm going to have a square base. And the other dimension that I'm missing is my y, right? My height. But I'm restricted to 48 feet of material, right? So check this out. Before, in example 1, I was restricted to my fencing, right? I was restricted to my 500 feet of fencing. Here I'm restricted to 48 feet squared of material. Cool. So what exactly does that mean? Well, that is talking about how much material I can cover my box with, right? I can use to make my box. And that refers to my surface area. Alright? So we're actually talking about the surface area. Let me actually write out the whole thing. Surface area of 48 feet squared, right? So I have 48 feet squared. So dimensions for area are always squared. So it's like, okay, what can I make with this, right? Is it going to be the area of the box or the surface area of the box? Well, in this case, we're using it to make the whole box, so it's going to be the surface area of the box. And then the question here, again, is what dimensions what we're looking for, x star and a y star, will result in a box with the largest volume. So we're actually trying to maximize here the volume, but we're being restricted by the surface area, right? So right there we have our 2 equations that we have identified, right? We're trying to maximize the volume. So volume in this case is going to be the square base times its height. So x squared times y is going to be the volume of this box, right? And then we're restricted by the surface area. So we actually need to go ahead and find out what the surface area of this box is, right? So we cannot maximize our volume because we have these 2 variables here. So we're going to go ahead and get rid of one. We're going to get rid of the x or the y to go ahead and maximize my volume, right? So same story, different type of problem. So here we have to find first the equation of the surface area, because that's not given to you. Well, the surface area is the area of every layer of my box, right? And I'm going to start with the bottom and the top, right? So the bottom and the top are exactly the same, right? And those are going to be x times x, or x squared. So my bottom and my top are always x squared, and I have 2 of those. I have a bottom and a top, so 2. And then the rest, what's left, is going to be my sides, which are something like this, or this guy right here. And they're all actually going to be the same as well because it is a square box. So there's actually 4 of those, a front, a side, another side, and a back. Those 4 are going to be, they're going to be 4 of those, and the area of each of those sides is going to be x times y. Okay? So now, somehow we're going to use that the surface area is equal to 48 feet, right? And somehow we need to choose here, what are we going to solve for? Are we going to solve for x, or are we going to solve for y? Well, looking at my equation of my surface area, I don't like this x squared here, right? Solving for x squareds or y squareds are annoying. So I have a nice y here to the first power that I'm actually going to want to solve for. So that means that I'm solving for y. To plug in y into here, right? I'm trying to plug the y in terms of x into the volume, so then I can go ahead and perform my maximum, my first derivative test, right? So first things first, I got to move over this guy to solve for my y. So I'm going to have 48 minus 2x squared equal to 4xy. Second, I need to get rid of this 4x in front of my y, so I'm going to go ahead and get y is equal to 48 minus 2x squared over x, 4x, right? So in this case, I didn't simplify my equation at first, but I know that 42, 2, and 4 are all divisible by the same number, and that number is going to be 2, so I'm going to divide everybody by 2, 24 minus x squared over 2x, right? So now that I have solved for my y, I am going to go ahead and plug it into here so I can go ahead and maximize my volume. So the stories kind of repeat. We just need to see different types of examples on how to do these problems. So now that I'm going to have x squared times 24 minus x squared over x, right, times that. Cool. Now I need to go ahead and simplify my volume equation so I don't do an unnecessary product rule. So that means that I'm going to multiply. I'm actually going to first reduce this x squared with this x, right? I have 2 x's on top, 1 x on the bottom. That means I'm going to cancel this x on the bottom. So I'm going to cancel one of these, leaving me with 1 x on top. So that's leaving me with 1 x on top with 24 minus x squared. And I'm going to go ahead and distribute that x. So I'm going to have 24x minus x cubed. Now that I have a nice polynomial to derive, I'm going to go ahead and do that. I'm going to go ahead and perform the first derivative test, which is going to be b prime is equal to 24 minus 2x squared. Cool. So now that I've done that, I'm going to set the volume equal to 0. So I'm going to have 24 minus 2x squared equal to 0. So I'm going to go ahead and solve for x, right? I'm going to have 24 equal to 2x squared. And then I'm going to divide both sides by 2. And now I'm going to go ahead and just square root both sides. So I know that if I square root both sides, I am forced to kind of get a plus or minus answer. But let's think about what we're doing. We're looking for a dimension of a length, right? And lengths are distances, and distances are never negative. So that means that I can never have a negative answer here. That just wouldn't make sense, right? So I'm going to go ahead and take that away because there's no point of having a negative dimension. I'm looking for the positive dimensions only, and my positive dimension is going to be square root of 12. But I'm not done. I need to go ahead and do my first derivative test by doing my number line, which I'm going to have a square root of 12, right? So square root of 12 is going to be, it's a little bigger than square root of 9, right, which is about 3, but it's smaller than square root of 16, which is about 4. So the number that I'm going to test to be bigger is going to be a 4 because it's less than square root of, this is equal to square root of 16. Or I'm going to test 0, which is equal to square root of 0, which is less than square root of square root of 12. Right? So if I plug in 0 into my v prime, which is right here, I will get a positive. And if I plug in square root of 16, or I plug in 4, I would actually get a negative. So since I'm going from positive to negative, I have a maximum. Therefore, this x value, this x dimension, maximizes my volume, right? I'm maximizing my volume. So that upgrades now to being my x star, right? So now that I have my x dimension, I need to go ahead and find my y dimension, which is going to be y star. And I find y star by plugging it into my equation for y. So I'm going to have 24 minus x squared, or x star squared, over 2 times x, right? And that is going to be me plugging in square root of 12. So that's going to be a little annoying to find this final answer, because the square root is going to cancel that 12, but it's going to be 12 over 2 times square root of 12, which is just 2 square root of 12, right? And that is going to be 12 over 2 square root of 12, or these two are going to cancel and give me 6 over square root of 12. But I can say that I'm nicely done now because I have found my dimensions, right? I can say that 6 over square root of 12 has me completely done. But let's go be like completely anal when it comes to being simplified. And let's just say that square root of 12 is actually not my final answer, because I can break down square root of 12 into square root of 4 and square root of 3. Therefore, my answer being 2 square root of 3. So my actual most simplified version of my x star is going to be 2x squared, 2 radical 3. So that means that I can break down this answer right here, and I can have 6 over 2 radical 3, right? In which these two cancel, so I get 3 over radical 3. But then again, I need to rationalize that function, and I need to have times square root of 3 times square root of 3. So my final answer actually becomes 3 square root of 3 over 3, which, I'm sorry, that's still not the answer. I need to cancel out these two, and I need to go ahead and just get square root of 3, right? So it's just square root of 3. So that means that my x coordinate is going to be 2 square root of 3, which is down here in the x star, and my y star is going to be just square root of 3. So I have found the dimensions that maximize my volume. So you guys can see that the rhythm of optimization is kind of the same. We're just going to go ahead and follow the same pattern of, figuring out what's going on. Then we're going to go ahead and apply it into figure out our formulas, and after we figure out our formulas, we just play with them to be able to derive, right? Our point is to be able to get here. Once we are able to just get here, just give me a second on that. Once we're able to get here, right, we're good to go. That is our main goal. Once we get there, we're good to go, because we can go ahead and take our derivative and just do what we know how to do already. The new stuff is everything above that, right? I would say, like, identifying which variable you need to solve for. So getting to here is a big checkpoint, right? Once you have solved for your variable and you're just going to plug it into your equation, you've gotten to a big checkpoint, right? So those are the two biggest checkpoints in your optimization problem. First, when you have totally solved for your variable, so in this case solving for y, and then once you plug it in and you have it ready to simplify, and you take your derivative, right? So those are your two big checkpoints when it comes to organization. But when you solve for the variable, and then when you're ready for your first derivative test. So now let's go to some practice problems on different types and variations of optimization problems. So see you guys next time.